Yeah, good morning. In the last class, we have discussed about various reactions which takes place in the box part of the blast furnace. In that, we have seen that the reduction of SiO2 to SiO by carbon, and also we have seen how the SiO gas is getting reduced by carbon and forming Si plus CO, where your silicon is joining in the metal phase. Similarly, we have also seen that reduction of sulfur. So sulfur is basically present in the form of CAS or FES in the blast furnace. Uh, for and this CAS reacts with the silicon monoxide and forms SiS plus CO. And this SiS again is a gas. When it travel upwards, will get dissociated into silicon plus sulfur. So this is how the silicon and the sulfur both will join the metal phase inside the blast furnace. Right? So beside these iron oxides, the other oxides also enter into the blast furnace wash region, such as we have P2O5, then MnO, SiO2. Okay, so these all comes from the your ore, and along with that, we also have CaO as well as MgO, which comes from the fluxes. So these oxides are easily get reduced by the reducing gas, that is carbon monoxide, at high temperatures, both direct as well as in the indirect form. So you can see in this particular slide, there we can see the MnO getting reduced by carbon monoxide. There is a slag. The MnO is present in the slag, and this is the reducing gas traveling upwards. So when the slag and the gas are come in contact with each other, so this kind of reduction basically takes place between the slag and the gas, and that is how your Mn will enter into the metal, and the CO2 is the gas which is formed after this reaction, and that again travels upwards. So at lower part of the blast furnaces, CO is highly stable, so it gets reduced by the oxides present in the slag, and it forms the manganese, silicon, and phosphorus like this, along with the carbon dioxide. Okay. So this CO2 again, as it is um, not stable at high temperatures, so it travels up, and it dissociates again. And this is how your manganese, silicon, and phosphorus will enter into the hot metal. Okay, so these are basically the indirect reduction reactions, and which is basically a slag gas interactions. Similarly, there are also some direct reduction reactions also takes place in the wash part of the blast furnace, where the oxides present in the slag, when the slag gets trickled down for the bed of coke bed, then the carbon is present in the coke will get interact with these oxides, and there is also provision of reduction in this way, where again same manganese, silicon, and phosphorus will join the metal phase, and the carbon monoxide gas is formed. So from the Ellingham diagram, we can understand this um, the the indirect as well as the direct reduction reactions, how it is happening. So at high temperatures, um, these um, at high temperatures, this oxides, the MnO and SiO2, will get reduced by uh, carbon. Okay, so you can see beyond this temperature, if you just plot a vertical down, so that will give the temperature. and beyond this temperature, there is a possibility of a reduction of these oxides by carbon in the direct form. And below these temperatures, okay, there is a possibility of reduction of these oxides by in index. So this is what we can understand from the element diagram. Since all the reactions are basically endothermic in nature, you can see by from the delta H values, we can understand these all reactions are endothermic in nature, as delta H values is positive. Okay, and these are all are favored by high temperature. Okay, and it happens only at the bottommost part of the blast furnace. And also, if you see the scenario of the burden inside the blast furnace, um, except coke, the rest of the iron, the rest of the product, the rest of the raw materials, sorry, the rest of the raw materials are undergone softening and melting at high temperatures. So the coke is the only one which is in solid state at a high temperature. So these smelted products, whatever are there, they get trickled down through the bed of coke solids, and during that time there will be an interaction between the solid carbon and the liquid product, and there is a possibility of reduction of these oxides with excess. And also from the Ellingham diagram, we can observe that you can see here the FeFeO line or is very close to very close to the phosphorus line. So that means how much amount of iron oxide get reduced in the blast furnace. A similar amount of phosphorus also get reduced inside the blast furnace. Means the most of the phosphorus will join the metal phase in the blast furnace, as these two lines are very close to each other. So there is a maximum reduction of P2O5 may take inside the blast furnace. So there is a possibility of 99.5% of iron is getting reduced. Also, complete reduction of phosphorus pentoxide also takes place in the at high temperatures inside the blast furnace. Along with these oxides, oxides like Al4, MgO, and CaO. So these are not easily get reducible. So when the slag travels to the lower Bosch region, so it gets dissolved these high melting oxides, making it more and more basic and more fluid. So upon smelting, the iron ore produces hot metal as well as slag, which cools down to the bed of coke solid, and it finally gets settled down in the hot part of the blast furnace. Similarly, if you see what are the reactions which takes place in the rear part of the blast furnace, where the combustion of the coke takes place in front of the tuyers, and this is the region which is having the maximum temperature inside the blast furnace, ranging from 1800 to approximately 2000 degrees centigrade. Temperature will be available at this particular region. So the blast furnace must produce a definite quantity of heat for each ton of iron production. So this basically the amount of heat which is required for this melting process takes place. That will be basically generated in front of the tuyers because of the combustion of the coke for combustion of coke, basically the formation of CO2, C plus O2 is CO2. There is an exothermic reaction which takes place in front of the tuyers, and that happens when heated air is subjected to subjected into the blast furnace, and the coke, whatever it is present in front of the tuyers, when it comes in contact with the created air, the carbon is present in the coke reacts with the oxygen is present in the air, and uh, and that is how uh, the reaction takes place. C plus CO2 is an external reaction. Um, so we basically send preheated air into the blast furnace so that the um, the raft temperature will be increased. So you can see here, basically the air consisting of around 23% of oxygen and 77% of nitrogen will be there. And when you allow this air to preheated air to enter into the blast furnace through the tuyers, then that will react with your carbon which is present in the smoke, and the reducing the acid will be formed. And this preheated air is basically produced in the checker bricks, in the BF blast furnace stoves, and the temperature of the preheated air will be around 800 to 1000 degrees centigrade in Indian scenario. So yeah, this is how actually the uh, preheated air is injected into the blast furnace through the tuyers, and also we are sending a PCI, that is pulverized coal injection, is also done, so that to lower down some of the consumptions. And if you see inside the blast furnace in front of the tuyers, we basically charge coke here. So when you are injecting this preheated air with high velocities, and this air, when it enters into the blast furnace, it pushes out the coke which is present exactly in front of the players, and because of which this kind of uh, this kind of gap will be formed. That is called as a raceway, where this is the region where the combustion of the coke basically takes place. So you can see a series of tuyers are arranged across the periphery of the um, blast furnace. Um, in front of every tuyer, there will be a raceway is basically formed, and this is the region where the combustion of the coke basically takes place. Okay. So the condition which is prevailing in front of the tuyers when the combustion of the coke, if you see in this raceway, there is a possibility of the circulation of when the reduction is happening, there is a circulation of the coke particles. Basically takes place within the raceway, and the combustion basically takes place, uh, which gives the formation of CO2, CO2, because at the initial stages, uh, once again, so in front of the figures, the reactions which are happening. If you see within the raceway itself, there are two zones are formed. You can see zone A as well as zone B. And in zone A, the reactions are carbon is present in the coke, reacts with the oxygen is present in the air, and forms CO2, that is carbon dioxide, which is an exothermic reaction. But at high temperatures, CO2 is not stable, which we can uh, which we can observe from this Elegum diagram. Okay. So at high temperatures, CO2 is unstable. Okay. So beyond this particular temperature, okay, around 650 to 700, at this temperature, CO2 is not stable. Okay. At high temperature, CO is stable, whereas at low temperature, CO2 is highly stable. So whatever the CO2 which is formed in front of the beer, it is very unstable. Okay, so this CO2, whatever is formed, that will readily again react with carbon and forms a carbon monoxide. Okay, that happens basically in the zone B, which is actually an endothermic reaction. So this kind of reaction basically takes place in the rest, and the reducing gas, whatever it is formed, that will basically travels upwards. Okay. So these tuyers are basically projected a little bit upwards, okay, so that that there is an easy provision of these reducing gases to travel in the upward direction. And in the same way, once the combustion has finished, again a similar quantity of coke will again come and fall into the raceway. Again, the reaction takes place, and the products, whatever is formed, the gaseous products will travel in the upward direction. Like this, there is a continuous movement of the coke takes place in front of the tuyers, and this kind of combustion reaction basically takes place in the raceway zone. So raceway is the area where you have a high temperatures are prevailing inside the blast furnace. So in the zone A, because of these chemical reactions, the gaseous environment is prevailing in the zone A and zone B. If you see, zone A consisting of primarily CO2, O2, as well as the N2. And in zone B, you will be having a gaseous phase which is predominantly consisting of CO2, CO, and N. So as I mentioned, that in zone A, this kind of reaction basically takes place. That is the carbon is present in the coke reacts with the gaseous oxygen and forms a carbon dioxide gas. Okay. So this is a highly exothermic reaction where you can see the delta H values. Okay. And this CO2 gas which enters into the zone B, and the at zone B, the depletion of oxygen basically takes place. Okay, because and CO2 reacts with carbon because this double reaction, there are large amount of carbon particles, and CO2 is not stable at above 1000 degrees centigrade, as I told you. So for this reason, if any CO2 forms, it will readily react with carbon and forms CO gas. And this is how the reaction takes place. And you see that this is another reaction where the delta H value is positive. Although this reaction absorbs a large proportion of heat is generated by the previous reaction, like this one, this reaction is also called as solution loss reaction, because the carbon which would otherwise be burned at the tuyers to produce heat is lost by reacting with CO2 gas. So this means increase in the coke consumption to overcome the loss of carbon as well as the loss of large amount of heat. Okay. So this reaction is also called as a border reaction, or we can also call this as a carbon gasification reaction. So the net result, if you see, if you just combine these two, and you can get the net result, that is 2C plus O2 gives rise to 2CO. So that is the net reaction, which is again an exothermic reaction. And any moisture, like sometimes to control the raft temperature, we basically send an amount of steam which is injected into the blast furnace to control the raft based by diabetic flame temperature. So in that case, the steam, there is H2O present, will react with the carbon which is present in the coke, solid carbon, and forms CO plus H2. So in this case, we get if 1 mole of carbon reacts with 1 mole of H2O, we get 2 moles of reducing gases. 1 mole of CO, 1 mole of H2. Both are reducing gases, and this is basically an endothermic reaction where you can see the delta H value is positive. And H2 which is formed that will both H2 as well as CO which is formed that will actually travel upwards. So similarly, if you see the reaction which takes place in the Hearth part of the blast furnace, so in the Hearth, What is Hearth is basically it is a sink for the liquid product. So the slag as well as the hot metal both get settled down in the Hearth part of the blast furnace. That is the liquid products, whatever is formed after the smelting process. Today, these liquid products get settled down in the Hearth part of the blast furnace. As the density of the slag is less than that of the hot metal, so it gets settled on the surface of the hot metal. So you can see the specific gravities of a slag and molten metal are around 2.5 and 7. So slag is basically float on the top of the molten metal and gets settled down in the hearth part of the blast furnace. So in the hearth part of the blast furnace, majorly there will be slag metal reactions which take place. And the composition of a hot metal, whatever it is formed, that will be having composition somewhere like this. It ranges from carbon 4 ranges from 4 to 4.5, silicon 1%, manganese 1%, phosphorus and sulfur almost 0.01 to 0.05 each. And similarly, composition of the slag, if you see, that consisting of majorly acetic oxides as well as basic oxides. So CaO, MgO, SiO, Al2O3, MnO, P2O5, and a small fraction of FeO will also be present. This is the overall chemistry or the composition of slag as well as the hot metal, which formed in the hearth part of the blast furnace. So in the hearth part, as I said, that the slag as well as the hot metal both get settled down in the hearth part, one on each other. So whatever the reaction which takes place inside the blast furnace at different parts, but final adjustment in the chemical composition of the hot metal as well as the slag will take place only in the hearth part of the blast furnace. So in the hearth part, we have hot metal as well as the solid central column solid coke, which is present in the blast furnace. So although most of the carbon is burnt in front of the tuyers, a certain amount of coke is descended into the hearth and deposited in dead man zone. That means there is a region where there is no region of the heat penetrated into the blast furnace. Okay. So whatever we have seen, these tuyers, raceway, whatever it is there in front of the tuyers, that will be present across the diameter of the blast furnace. But this heat cannot be penetrated toward the center of the blast furnace. So at the center, whatever the coke is there, that will be in unreduced condition, which will not participate in the combustion process. That is called as the dead man zone, where there is no reaction basically takes place. So So since the metallic iron in the blast furnace hearth remains in contact with this carbon in the coke, in the dead man zone, sufficient longer time before you tap it from the blast furnace. So there is a possibility of dissolution of this carbon into the metal may take place. So that is how you can see around 4.5% of carbon in the hot metal. Just because of there is a solid diffusion of carbon base taking place from the solid carbon from the coke into the hot metal. And similarly, there is a possibility of some of the slag metal reactions may take place inside the heart part of the blast furnace. That is, the MnO, which is present in the slag, will react with the carbon, which is present in the hot metal, and this is how the MnO get reduced, and Mn will travels into the hot metal. So this is basically these all are all the chemical reactions which takes place inside the blast furnace are heat and mass transfer driven reactions. So this is how the MnO is getting transferred from the slag to the metal. So it is basically a mass transfer reaction. Similarly, the oxygen is present in the MnO is reacting with the carbon and it is forming GO gas. So as the density of the slag is getting increases, there is a sharp increase in activity of MnO in the slag. So that is how the MnO basically reacts with the carbon and the reaction will proceed in the forward direction. Similarly, silicon reaction, the SiO2 is present in the slag, the reaction with the carbon is present in the hot metal, and This is how the silicon also will transfer from the slag to the metal. Similarly, sulfur. Sulfur, as I told you that sulfur will present either in the form of CAS or FES form. So sulfur is present in the combined state. Sulfur always present in the combined state in form of FES or CAS. So this sulfur will react with this is the sulfur is present in the metal, reacts with the CaO which is present in the slag, and it forms FeO plus CaS. So this is how the sulfur will join from metal to the slag phase. And now this Fe, whatever it is formed, that again reacts with carbon present in the hot metal and forms Fe plus Ca. So if you just combine these two reactions, then certainly you will get this kind of combined reaction, that is FeS plus Ca plus C, so Fe plus Gas plus C. So this is how the Fe enters into the metal, and sulfur enters into the slag, so as the other reducing gases form. And this is basically again an endothermic reaction. The enormous amount of heat is required for this reaction to carry forward in the pro direction. So if you see the conditions for the desulfurization, because desulfurization can effectively take place only in the blast furnace. So the conditions are, first one is the high temperature. We require high temperature for removal of sulfur in the blast furnace because, as I just now told you, that this is an endothermic reaction. This kind of reaction is endothermic reaction. So for these reactions to accelerate in the forward direction, we require high temperatures. High temperatures are necessary for the removal of sulfur in the blast furnace. Similarly, we require a basic slag. We require a basic slag for the effective removal of the sulfur. Yes. So we can see here, we can see here as well as here also you can see FeS is getting reduced by burnt light or calcium oxide. So the more the basicity of the slag, or then there is a high possibility of recovery of sulfur from the hot metal matrix. This hot metal, we can extract maximum amount of sulfur from metal. Reducing atmospheres. Reducing atmosphere is required for reduction of FeO, because if the concentration of FeO in the slag is getting improved or increased, then there is a possibility that this reaction can move in the backward direction. Okay, so to suppress the backward reaction, what we are doing is that this FeO is getting reduced by carbon, such that the activity of FeO in the slag is reduced, so that this reaction cannot move in the backward direction. So that's why for effective desulfurization, we require reducing environment. Similarly, good fluidity of slag is also necessary, because the rate of diffusion of these reactants and products basically depends upon the viscosity of the slag. And again, viscosity of slag again depends upon the composition as well as the temperature. So hence, increase in the diffusion rate, or if you want to improve the desulfurization rate, so that can be achieved only by increasing the temperature as well as decreasing the viscosity of the slag. If you are decreasing the viscosity of the slag, certainly the fluidity of the slag will be improved. So good fluidity of the slag is very much necessary. Similarly, high silicon content in the metal. So that again, same silicon, what is the carbon which is doing here, the same silicon will also do. The silicon will reduce the FeO, so that the concentration of the FeO in the slag can be suppressed, or because the activity of the FeO slag can be suppressed as the concentration is decreasing, so that this reaction cannot move in the backward direction. So these are some of the conditions for the effective desulfurization in the blast furnace. Now, blast furnace slag. Basically, slag is basically a combination of flux and the gangue. So the combined molten oxides, which are the product of a smelting and refining process, are basically known as slag. And a slag should at least consist of one basic oxide and then one acidic oxide. Then only we can say it as a slag. And you can see these oxides are basically categorized into three ways. One is acidic oxide, another one is basic oxides, and third one is amphotic oxides. So SiO2, P2O5, PiO2, B2, P2O5, B2O3, these all are acidic oxides. And we have basic oxides like CaO, MgO, FeO, MnO, Na2O, K2O. These are all basic oxides. And amphoteric is sometimes it acts both acidic as well as basic based upon its composition. So there is Al2O3, Cr2O3, V2O3. These are some of the amphoteric oxides. So basicity is nothing but the ratio of summation of all the basic oxides to that of the acidic oxides. So we basically add basic oxide based upon the composition of the or the amount of acidic oxide present inside the or joining into the blast furnace by both to the raw material as well as from the coke ash. So to improve the fluidity of the slag, so depends upon the composition, depends upon the quantity of these acidic oxide which are joining into the slag phase. We add a similar quantity of basic oxides to maintain a good basicity, so that the viscosity of the slag will be nominal. So we define slags into two categories. One is acidic slag, and one is basic slag. Other one is a neutral slag also there. So if the basicity is less than 1, then we call it as a acidic slag. That means in that case the composition of or you can say the concentration of acidic oxide in the slag will be more compared to that of the basic oxides. There is the V ratio. And basic slag means when the basicity is greater than 1, then it's called as basic slag. That means the concentration of basic oxides is greater than that of the acidic oxides. Neutral slag means where the basicity is equal to 1. So as I said that at any slag composition, its viscosity decreases with increasing temperature to obtain a fluid free running slag. A minimum Hearth temperature is required, which is called as a critical Hearth temperature. It should be as low as possible to cut down the Hearth requirement as well as to increase the Hearth lining life. The first slag in the blast furnace forms in the Bosch region at around 1200 degrees centigrade, and it is known as Bosch slag. And melting in such a low temperature is only possible because of the formation of the low melting compound, that is FeO and SiO2, large amounts. It has low liquidous temperature. This is known as a primary slag. So as the primary slag trickles down to the bed of solids, the temperature rises and FeO gets reduced and slag dissolves more CaO. At tuyers, the coke burns, thereby releasing coke ash containing SiO2 and Al2O3. This makes the slag at the tuyer level high in SiO2. Final composition adjustment occurs during the passage of Bosch slag into the earth, during which FeO content becomes very low. So the final adjustments basically takes place in the Hearth part of the blast furnace. This is all about these reactions in the blast furnace and the products that are formed in the blast furnace. In the next class, we will discuss some other aspects.